In Lesson 2.3, the product and quotient rules and higher order derivatives, we'll be talking about two more crucial derivative rules that we haven't yet discussed back in Lesson 2.2. That, of course, would be the product rule and the quotient rule. After we learn about those rules, we'll apply them to a few examples, and then we'll talk about higher order derivatives. Derivatives don't have to stop after just one differentiation. We can differentiate as many times as we like, and we'll talk about that. We'll finish this lesson up by talking about the trigonometric derivative rules for the remaining four elementary trig functions, and then we'll do a cool little example where we just look at graphs and try to determine what's the original graph, what's the derivative, what's the second derivative, and so on. So all that being said, why don't we go ahead and take a look at these two additional rules we have to deal with. Let's go ahead and formalize those now. In Lesson 2.2, when we were dealing with basic differentiation rules, one of the rules we covered involved scalar multiples. If there is a constant multiplying a function, all we had to do was move the constant out of the way and differentiate the function that remained. However, that is not the case when we're multiplying two functions together. See, if there's a constant, we can move it, but two functions, there's no such easy rule. You might think maybe we could do the same thing that we did with the sum and difference rules, where we just differentiate each function separately, but that doesn't apply when the two functions are multiplying. So let me just go ahead and run the product rule by you. If we are differentiating a product of two functions, all we really need to do is let each of the functions take a turn being differentiated. And so we'd end up with that as our first grand term, and we'd end up with this as our second grand term. Notice that you could memorize derivative of the first times the second, plus the first times the derivative of the second. A lot of students in the past have memorized these kitschy little things. But really all that's going on is we're letting each function that is in the product take a turn being differentiated. Imagine what would happen if we were trying to differentiate a product of three functions, f, g, and h. That actually would not be that difficult. We'd simply differentiate the first in one term, we'd differentiate the second in another term, and then we'd differentiate the last in our last term. So you can see that we can extend this to any number of products. Just let each function take a turn. No big deal. So that's going to move us to our quotient rule. And to be perfectly honest, after we get through the next lesson, 2.4, you'll be able to prove this quotient rule that I'm about to show you by simply thinking of the quotient in terms of this, f of x times 1 over g of x. And then we could do the product rule to that. However, it's a little bit more involved. We really need to learn the chain rule before we go about doing this. So don't worry about this right now. Let me go ahead and tell you what the quotient rule is. And again, many students memorize this in many different ways. But no matter how you memorize it, it's always going to look like this. We're going to do the denominator times the derivative of the numerator subtracted by the numerator times the derivative of the denominator, and we're going to divide all that by the denominator squared, which would look like this. Now many students that I've come in contact with memorize low d high minus high d low over low low. Now I find that to be kind of ridiculous myself, but if it works, it works. What they basically do is they say low d high, you see it there, low d high, minus high d low over low low. I don't care how you memorize it, it doesn't matter to me, but be sure you know how to use the quotient rule. It's a very common thing to have to use here in calculus. So with that, let's go ahead and take a look at a few examples where we apply these two new differentiation rules and see how they work out. In example A, we have a pretty obvious example of the necessity of the product rule. Here we have two terms that are being multiplied. So if we want to go ahead and apply the product rule to this, our derivative will simply be the derivative of the first function, which in this case is just 6, and the second function just tags along. And then I will add, this time I'll keep the first function, but differentiate the second one, which would give me 3x squared. So there's my derivative. Now I know some of you are going to want to multiply this out and simplify and all that good stuff. So if you are one of those people, here is what this is going to look like if I distribute. And finally, once I do that, I can go ahead combine my like terms, and it looks like I'll have 24x cubed plus 15x squared minus 12. So you see, the product rule is not that difficult. You simply let each of the two products take a turn being differentiated, and really you don't even need to simplify at the end, although you can if you choose. Now some of you might remember back in lesson 2.2, I made a very strong point about needing to simplify a function before you differentiate. Well, if I did multiply this function out, let me show you what we would get. This would actually give me 6x to the fourth power plus 5x cubed minus 12x minus 10. Had you done that first and then differentiated, what would your result be? Well, let's see. This would give us 24x cubed, which sounds very familiar. This next term would give us 15x squared, also sounds very familiar. This would give us negative 12, which is right there. And then, of course, the minus 10 would just differentiate away to nowhere. So, which way would you have done it? Would you have wanted to multiply this out and then differentiate? Or would you have wanted to use the product rule? Quite honestly, either one works here. Both very nice and not too difficult of a problem. However, when we get to example B, we'll see that multiplying the product out is not always a feasible way to do this, and that will necessitate the use of the product rule. Watch. Alright, so here is a product of two functions that cannot be simplified. We're not going to be able to multiply these together in any way. Although if we want to, we could rewrite this. It's not going to make too much of a difference, but we could call it x to the 1/2 multiplied by sine x. At least now we've torn the two products apart, so the product rule might be a little bit obvious now. So let's go ahead and try this. The derivative of our function is going to be the derivative of the first part of the function times the second part of the function. So there's our first term. And then, of course, for the second part, we'll have to use the derivative of sine, which, as we learned in the last lesson, is just cosine x. So there it is. Some of you are probably going to want to rewrite this for whatever reason. And if you want to do that, that's fine, as long as you do it correctly. Don't make any mistakes. And so we end up with this as our derivative. So you can see that not always is it possible to simplify before differentiating, and really never do you need to simplify after differentiating, although that's your choice. You can do it if you like. Just as I said, make sure you don't make any mistakes in the process, because you will get dinged for them at the end. So, alright, we've done two problems now with the product rule. I think it's about high time we take a look at a problem that uses the quotient rule. Example C. Wow, this is a pretty brutal looking quotient thing. Well, regardless of that, it certainly is a quotient, so we can differentiate this using the quotient rule. And if we do that, let's see exactly how this is going to work. The derivative of f of t, well, if we do this, we're going to do the bottom, the denominator, multiplied by the derivative of the numerator, which is going to be 4t minus 5. You can verify that yourself. Subtracted by the numerator times the derivative of the denominator, which in this case is actually just 2. And then we're going to divide that entire mess by the denominator squared. And there you go. There's your quotient rule. Now, if you want, we can go ahead and simplify this. I know a lot of you still have that simplification bug in you from previous math courses where everything needs to be simplified. So if we do that, well, go ahead and pause the video. Try it yourself if you like. But I assure you that the numerator is going to boil down to 4t squared plus 4t plus 1. And you can verify that yourself if you choose. I only simplified the numerator, so the denominator is going to stay the same. and we end up with that. Now some of you might look at this and say, oh, but wait a minute. The top, the numerator, looks like it's going to factor. And in fact, the numerator does factor. In this case, it factors to, oh wow, check this out. Quantity 2t plus 1 squared. And then in the denominator, we still have 2t plus 1 quantity squared. That's very interesting. So it appears that the derivative of this nasty, nasty looking function is actually just 1. Wow. Well, that's very interesting. But again, some of you might have said to yourself, well, couldn't we have simplified this function before differentiating? We could have avoided the quotient rule, could have made things a lot easier. Well, let's see what had happened if we did do that. If you chose to factor and cancel or divide this before you began, however you chose to do it, what you actually would have ended up with, this is logically equivalent to t minus 3. That's it, just t minus 3. And what's the derivative of t minus 3? Well, of course, the derivative of that is just 1. So you see that simplifying before you differentiate actually does make a lot of sense in certain cases. Makes your work a lot easier. The quotient rule is not going to be your best friend, I promise you. It's important, you will need to use it, but you're not always going to love using it like you do everything else. So if you can simplify before you begin, absolutely try to do that. And you see that, especially in this example here, would have made your work a lot easier. Well, let's take a look at example D, where I will challenge you to simplify it before we begin, and if you take that challenge, you will fail. Let's take a look at example D. Alright, so even though you can't simplify example D before we begin, I'm still going to posit that it's not a very difficult problem to do. If we want to differentiate this function, f of alpha, remember once again that we're going to start by looking at the bottom, or the denominator, times the derivative of the numerator. Again, don't forget that cosine becomes negative sine. And then we'll subtract the numerator multiplied by the derivative of the denominator, which in this case is 3 alpha squared. And we'll divide that whole mass by the denominator squared, which in this case will be alpha to the 6th. Now we could stop there, say we're done, everything looks fine, don't really need to simplify. However, again, I know a lot of you like to simplify, so if you are one of those people, here we go. We have negative alpha cubed sine alpha. We have, this will be minus 3 alpha squared cosine alpha. And again, we'll have alpha to the 6th on bottom. And some of you are going to say, well, that's not fully simplified yet. Every term has alphas in it. So you want to cancel out the alphas? All right, let's cancel out the alphas, no problem. We have alpha squared that we can factor out of each term. And that'll leave us with negative alpha sine alpha. Over here we'll have minus 3 cosine alpha. So we factored out the alpha squared. And if we factor out alpha squared on the bottom, we have alpha to the 4th. So if you want simplification, there you go. It doesn't get much simpler than that, not with these sines and cosines floating around. Although some of you might choose to split up the two terms in the numerator and divide each one by alpha to the 4th. Again, be my guest. As long as you do it right, your result will be correct. However, I'm going to stop here and say it's not really worth our time, because now I want to take a look at example E. So, although it might be torturous, example E is by no means undoable. In fact, it's not even that difficult. It's just, well, torturous. So if we take a look at this, clearly we're going to be using the quotient rule to differentiate this. Well, let's just go ahead and get started and see how this looks. If we want to do the derivative, we'll start by looking at the denominator multiplied by the derivative of the numerator. Now that's going to be kind of ugly in itself, because to differentiate the numerator, we're going to need the product rule. And so the product rule is going to look like this. The first term differentiated will be 2x minus 1, and then I just drag the second term along. And then I'll add that to another one where I keep the first term, x squared minus x, and differentiate the second term, which in this case is just 3. So again, torturous, yes, but certainly not undoable. Now the second part of this, the quotient rule, is the bottom derivative of the top, and then I'm going to subtract the top times the derivative of the bottom. And it appears like I'm going to run out of room here. Let's see how it looks. X squared minus x and 3x plus 4. And that's going to bring me to the edge of the screen. Well, what's the derivative of the denominator? Derivative of cosine? And we've talked many times, the derivative of cosine is actually negative sine. So, well, the negative will change this into a positive, and I'll just throw a sign in here to deal with all that. Alright, so it was ugly, and I'm going to divide it all by something that's not quite so bad, just cosine squared of x. Alright, well, I will leave this as an activity for you to accomplish. Just need you to multiply all this out if you want, simplify it all you like. If you want to, I'm going to show you the result here in just a moment, so if you pause the video, try it on your own. I know it's going to take you a minute. But when you're ready, here's what the result should look like. We should end up with cosine x multiplied by the quadratic 9x squared. And again, all I did was just simplified all those nasty things going on in there. There it is, 9x squared plus 2x minus 4. And then the second part of that in the numerator is just going to say sine x multiplied by, this would be 3x cubed plus x squared minus 4x. Now, I only messed around with the numerator, so the denominator is going to stay the same. No change here, that's still going to be cosine squared x. Now, we can't cancel out cosines, don't even attempt that. In fact, there's nothing more we can do to this. This is as simple as the derivative is going to get. Now, you might have asked yourself, what would have happened had we multiplied the numerator out before differentiating? Certainly, that would have saved all of this product rule stuff going on. Well, let me show you what would have happened. If I choose to simplify the top before beginning, what I actually would have gotten here would have been 3x cubed plus x squared minus 4x divided by cosine x in the denominator. Now this is very interesting. Had we done the quotient rule to this, look how it would have ended up. There's the denominator, and certainly this nastiness is the derivative of the numerator. And then we would have had the numerator written again. There's the derivative of the denominator. So maybe it would have been easier to simplify this function before differentiating, but it was fun for us to try the product rule and quotient rule all in one problem. Fun and exciting. That's all we're going for here. So with that, let's take a look at example F, which is going to be a big come down from the torturous nature of example E. Let's give it a shot. So although example F has a couple trig functions in it, don't let that scare you. First off, can we simplify this in any way? T sine of t plus cosine of t. There's no way that I'm aware of simplifying this. So let's just jump straight into the derivative. F prime of t. Well, for the first term, I see that we are going to have to use the product rule. So here is the t multiplied by the derivative of sine, which is cosine t. And we'll add that to the derivative of t, which is just 1, times the sine of t. Nothing is going on there but the product rule, so that shouldn't bother you too much. Now we have this cosine t, this term that's just kind of hanging out on its own. If we take a look at that, what's the derivative of cosine? Well, of course, that is negative sine. So there we go. If we do want to go ahead and clean this up some, and this is a problem that cleaning it up will actually make it a little bit easier. We have t cosine of t. This will be plus sine of t. And this is minus sine of t. Do you see why we simplified it? Look what's happening to these two terms. And so the derivative of this original function is simply going to be t times the cosine of t. That's not too bad. It actually looks like the derivative is easier to deal with than the original function. Sometimes that's the case, sometimes not. It's not really any observation you want to make in the future, but we'll talk a little bit about that in just a moment. Anyhow, now that we've done a few examples of using the product and quotient rules, let me make clear to you that there's no reason that you can only differentiate a function one time. The truth of the matter is, you can differentiate a function as many times as you like. In examples G and H, we're going to take a look at second derivatives. And we'll see that they're actually not too bad to deal with. Here we go. Before working on any problems involving higher order derivatives, let me first discuss what the whole point of doing this would be. Recall what a derivative is. It's simply the rate of change of a function. So what would a second derivative be? Not too much imagination will tell you it's the rate of change of the rate of change of a function. Or you could say it's the rate of change of the derivative, if you like. Now, at first that might seem kind of trivial. Why would we want to know the rate of change of a derivative? Isn't the derivative already a rate of change? And yes, that is true. And we will learn later many examples of a second derivative. Perhaps in physics you've already learned one. If you start by knowing the position of an object, if you differentiate the position, you'll end up with the velocity. And that makes sense even without knowing physics. What is the velocity? It's how fast the position is changing. Now, what if we found the rate of change of velocity? What would that tell us? Again, maybe you've covered this in physics. If not, you will. But that would actually tell us the acceleration of an object. So when you accelerate in your car, what you're really doing is changing your velocity. And what is your velocity doing? It's changing your position. So you can see how it all kind of fits together. Now, if we take a look at this function right here, we can consider this function to be the position of some particle or another. And if we're looking for the second derivative of it, we're just looking for what's the acceleration of that object. This notation might confuse you a little, this d squared over dx squared, but don't let it confuse you too much. Just remember that d dx means the derivative. So all we're really doing here is the derivative of the function. And if we treat dx as one unit, you can see how we'd have d squared in the numerator and a dx squared in the denominator. Normal notation, we just leave the parentheses off, but if we did it like this, perhaps it would make a little bit more sense. Regardless of that, to find the second derivative, we simply start by finding the first derivative. So let's take a look. Our function, which I am going to simplify before we begin because I don't want to use the quotient rule, our function is actually x to the 3/2 power minus 4x. That's an easy function to deal with, no big deal. So let's take a look at the first derivative of the function. Again, that should be no big deal either. That's just 3/2 x to the 1/2 minus 4. So there's our first derivative. Now, if we want the second derivative, notice that there are two tick marks here. How are we going to do that? Well, we're just going to differentiate the first derivative. And if we do that, we'll get 3/4 x to the negative 1/2, and the minus 4 essentially disappears. So there we go. If you want to rewrite this, if you're one of those people, that's fine. This is 3/4 square root of x, if you like. And that is the second derivative of our original function. Well, let's take a look at one more second derivative. But before we do, let's finish up looking at our 4 remaining elementary trig functions, look at their derivatives, and that will enable us to have better success at example H. So let's take a look at that right now. Alright, so as promised, there are the remaining 4 elementary trig functions that we need to learn the derivative rules for. None of these are very difficult, but you will need to know them, just like you already know the derivative of sine x and cosine x. The derivative of tangent x. If we remember that tangent x is simply sine x over cosine x, then really all we need to do is the quotient rule to find out what the derivative of tangent x is. I encourage you to pause the video right now and give it a quick shot, see what you end up with. I may ask you to prove this later on a quiz or test, so it's a good exercise. Anyway, if you do it correctly, what you should end up with is that the derivative of tangent x is actually secant squared x. Interesting. And the derivative of cotangent, well, remember the same thing again. Cotangent is simply cosine x over sine x. So do the quotient rule to that. And what you'll find out is that we get negative cosecant squared x. Now be very careful. The derivative of the derivative of tangent and the derivative of cotangent are not reciprocals the way that tangent and cotangent are, so don't get into the habit of thinking that. Know that the derivative of tangent is secant squared, and the derivative of cotangent is negative cosecant squared. Alright, well now that you do know that, if you recall that secant x is simply 1 over cosine x, then once again, all you need to do is the quotient rule, and you'll find out that the derivative of secant x, strangely enough, is actually secant x multiplied by tangent x. So it actually got quite uglier, but you need to know it. So my advice, actually do the quotient rule and get it in your head how and why this works. What's the derivative of cosecant x then? Well, that's actually going to be negative cosecant x cotangent x. Few observations that you might want to make. Notice that all the cofunctions are friends with each other. The cotangent is a negative cosecant squared. The cosecant has cosecant and cotangent in it. So they're all friends. Same with tangent and secant. Those are friends. But a more astute observation, because I did tell you in the last lesson that most students have trouble remembering the positive or negatives. Whenever you differentiate a cofunction, whether it be cosine, cotangent, or cosecant, you're always going to introduce a negative. With the sine, tangent, and secant, you do not. You leave that alone. So any cofunction is going to become negative when you do its derivative. Just memorize these, see where they come from, become familiar with them. And with that, now we can take a look at example H. In example H, what appears to be a seemingly easy problem could spiral out of control if you don't keep organized with your work. Remember that when we say the second derivative of secant x, what we're really saying is the derivative of the derivative of secant x. And that's quite fortunate because the derivative of secant x is something that we already know. In fact, we just talked about that, 30 seconds ago? So go ahead, look at your box if you need to. But the derivative of secant x is nothing more than just secant x multiplied by tangent x. And now this problem is going to become fun. Because to do the derivative of secant x tangent x, we're clearly going to need the product rule. Try to work ahead of me. See if you can get this before I get there. So if we do this, the derivative of secant x tangent x, I'll first differentiate the secant x part of it. And when I do that, that will give me secant x tangent x again. And I'll leave the second part of this, the tangent x, alone. So again, that differentiates to that, and I leave that alone. Now the second part of this will be where I leave the secant x alone and differentiate the tangent x. Fortunately, differentiating tangent x is not quite so long and drawn out. It's just going to be secant squared. So if we want to go ahead and simplify this now, we certainly can. This will give us secant x multiplied by tangent squared x, and this other term will simply be secant cubed x. Now some of you see secant x's in both terms, and you might want to factor that out. You certainly don't need to, but if you want to, you can. We'll have secant x multiplied by tangent squared x plus secant squared x. So that didn't really accomplish a whole lot. Maybe there's an identity based around that. I'll let you determine that for yourself. But that is our second derivative of secant x. Should you memorize second derivatives? Absolutely not. That's nonsense. But if you know the first derivative rules, you can always come up with the second derivative just by redifferentiating again. Well, all that being done, let's take a look at one more example. We won't have to do much math. It's more of a conceptual type of problem involving graphs. Let's take a look at it here. So in example I, we're given three graphs, and we need to determine which of these three graphs is f. Which of these three graphs is f's derivative, and which of these graphs is f's second derivative, f prime and f double prime. So how are we going to go about doing this? Well, I wish to remind you of the power rule, which we learned back in the last lesson. And if you recall, we learned that the derivative of x to the nth power is a function that has a power that is 1 less. So what this means is that if we have a cubic function, x to the third, the derivative of that will actually be an x squared type of function. And if we have an x squared type of function, the derivative of that would be just an x. That would be linear. And then a linear function would differentiate to a constant. And a constant, as we already learned, differentiates down to 0. So knowing all this, if we look at the graphs of functions, each time we differentiate, that graph is going to lose one of its humps. That being said, if you look at these three graphs, which graph seems to be the most complex, or with the most humps, if you will? And clearly that's going to be this red inverted parabola. That's probably a negative x squared type of function. So if we were to differentiate this, of course, as we said, it's going to lose a hump. And so what is it going to turn into? Both of these blue functions are linear, but notice that this linear function has a negative slope. Okay, well, that is actually going to be our first derivative. And the reason for that, from negative infinity up to whatever point this is, the parabola is increasing, and notice that the derivative is positive, the dark blue. After that, the parabola is decreasing, and the dark blue is negative. So clearly the dark blue has to be the derivative of this inverted parabola. Now, what is the slope of this dark blue line? I bet if you count carefully, you'll find that the slope of that is negative 4. And take a look at this light blue line. It is the constant function y equals negative 4. It is the derivative of the derivative, which we're going to call the second derivative. So in the last lesson, you had some practice drawing the derivatives of graphs, and now that the derivatives are already drawn, we just have to identify which is which. Just remember that every time you differentiate, the graph is going to lose a hump. So, in this lesson, we've covered many things. We started by looking at the product rule and the quotient rule, two additional rules that are very important and that you will need throughout the course of this year. We'll learn another rule in the next lesson that will also be very important. But after learning the product and quotient rules, we applied those to a number of problems. We talked about when it's important to simplify, which pretty much is whenever you feel like, or whenever you feel it'll make the work easier. After that, we looked at second order derivatives. And of course, from there, we could even go to higher order, third, fourth, fifth derivatives. We could go ad infinitum if we like. After that, we looked at a few more of the trigonometric rules that you need to know, so go ahead and memorize those. And we finished up by looking at some graphs. So again, we've covered a lot of stuff this lesson, but be sure to look back over your notes, make sure you're comfortable with everything, and good luck on your homework.